Alexander left, but we need help to set him up.
That should come up in a minute. Now, the bulb is at about half power. So,
Okay. But if you
it doesn't get much better than that right now. Paul's got a new one on order, but yeah, we'll need all lights off. We might even want the window closed.
So we're usually talking about bright science in the dark room.
Yeah, we should.
Yeah. If you take responsibility to take the it may fail. It's not the idea in classroom and laptop. It's hoping after 20 minutes work resources.
I think it's a matter of a requirement that every student has to turn into.
No, I don't think we make it a requirement. Again, with the education side and the physics side spreading so much, but sometimes that doesn't work. It's pushing it.
I remember when I was in graduate school, there was something like a faculty that they monitors that they sort of ask graduates who want to attend athletic curriculum. It's not really a requirement, but it's really one.
Everybody knows the cookies were here, they were not well advertised.
Okay, probably it's time to start. Let me opened this seminar by permission of physics seminar coordinator, Professor Alexander Wagner. So if you came for science and the community, you deserve the 2 points of attraction. And today's speaker is a special speaker in the sense that it is a big rare opportunities and big honor from the Department of Physics to presenters at the early stage of the career, which is departmental centers are typically the later stages. So today's speaker is very student at the Department of Chemistry, not Chem, materials, nanotechnology, also partially affiliated with the Department of Chemistry and Biochemistry. Forde, he joined NDSU in 2017 and immediately started a research program doing studies of popular new materials, light-halide perovskites. So he was presenting his results on like more than half dozen scientific conferences and did, I don't know, like 4 or 5 already accepted papers. With last one was at the Journal of American Chemical Society, which is highly competitive and corresponds about to physical regulators and physics community. So recently he focused his attention on a new class of phenomena in this materials, so-called Polarons. Well, it is not new generally for semiconductor materials, but it is new topic for this kind of materials, and any step is interesting. So everyone of these ideas is welcome to follow and ask questions, and the floor is yours.
Thanks, Dimitri, for the introduction, and thanks to the physics department for the invitation to talk to everyone here. As Dimitri said earlier, I am part of the Materials and Nanotechnology program on campus, and my undergrad background is in materials and nanotech as well. I mostly have an applied physics focus to most of the materials research I do, and I like to, well, since my graduate degree, I wasn't in computational too much until I got accepted into Dimitri's group. I had more experimental background. And I also do some experimental background with Dr. Hobby's lab on these materials too. So basically what I like to do is compute and measure interesting observables for photoexcited states. So you can see that we have a photoexcited electron hole, and there's possibility of, if you're in a semiconductor, you get excited above the bandgap, you could have a carrier cooling. So this dissipates the excess energy to the band edges. And controlling this is interesting for materials such as photovoltaics or LEDs. For LEDs, you want to manipulate them to be very fast carrier cooling to the band edges. And where photovoltaics, it's advantage to have extended carrier cooling. So that's one reason to want to model carrier cooling. And radiative and non-radiative recombinations correspond to like how efficient the light emitters you can have. So generally, if you're looking for something that's very bright, you want something that has very slow non-radiative recombination or very fast radiative recombination between the states. So you can get, so you put in 100 photons of energy, and then if it's 100% efficient, you get 100 photons back out. But you can also have some non-radiative decays too. So that's kind of where we're going after here. And so the title of this presentation, where we're going to be going, is previously published, or in the previous publication, we showed that in these perovskite nanocrystals or materials, you can have slow carrier cooling towards the band edges for a photoexcited electron. And the slow cooling corresponds to a region where it could be manipulated to perhaps invert it into an IR emitter, because you have the right energetic gas. And you have the slow cooling, so it might be possible to have the radiative recombination timescales to be competitive, so you can turn it into an emission source potentially. And so that's what we're trying to do with the Polaron model in these systems. And so this is just a broad introduction that will be guiding through the rest of the presentation. So introduction, what are nanocrystals and why do we care about them, and some simple physics to understand them. So general reasons to care about them is that they can be used for a lot of technology purposes. They're very versatile, so a lot of the popular nanotechnology devices, if you can make them in solution and deposit them in thin films, so you can make LEDs for light emitters, photovoltaics. People are also looking into using this charge storages for battery anodes. So you have energy devices, you can use them as sensors. So if you have a nanocrystal, it has a large surface area to volume ratio, so any sort of molecule that absorb out of the surface, you can get enhanced signal out of them, so for biosignaling or other types of sensors they're possibly used for. And there's also research into you can get long enough coherence times in the nanocrystals to use them as for quantum information as qubits as well. So there's a lot of technologies that they can potentially use for. And lead-halide perovskites, people have been looking into using them for all these applications. And so this is just a general idea of polyorganic cesium lead-halide perovskite nanocrystals. And so this top panel shows that they're made in solution, so they're colloidal suspensions. And this is just a general outline of how they're made. And these two figures come from Dr. Hobby's lab, where so this is what immediately after you make them, it's just a suspended solution. You have to purify them a little bit. You get nice clean samples of nanocrystals. And you can see just from ambient light, you can get pretty intense emission out of those because they do emit from in the green spectrum. And this figure just shows the general crystal structure of these materials. So the crystal structure is called perovskite. It's a type of mineral that people use for a while. And this is just the general mineral structure where the lead atom occupies or is coordinated to halide ions octahedrally. So lead in the middle, and then you have, in this case, bromine, but you can have other halides as well. And these big red ones, those are just space fillers to make the crystal structure stable. So that's what cesium does. And so the first paper to publish about these came out in 2015. Or they're the first ones to make nanocrystals out of materials. And they found that these materials are very versatile because they have very narrow PL line widths. They have high quantum yields that you can tune the color spectrum or the emission spectrum of these materials by changing halide content and quantization. So this figure is from the paper, or the original paper on these materials. You can make colloidal solutions spanning all the way from 400 to 700 nanometer in the UV Phys. And then this is just them showing the line widths, all the possible color schemes you can make. They have very fast lifetime, which is good for having high quantum yields for 50 to 90%. And then this figure shows potential applications for putting these, using these quantum dots for television displays. And so this kind of piano-looking figure is, I'm not exactly sure how it's made, but it's used to standardize like color purity for television samples. So these white dotted lines correspond to like the current limitations for like the current usage for TVs. Color purity of samples, and these black dots on the outside show are from the perovskite samples, and those indicate that they are very high color pure samples, which just comes from their very narrow line widths. So you can get intense green, intense blue, and intense red. So you can make very good LEDs out of these. And this just shows since 2015 they've had an insane amount of citations, so it's a very popular field to be in. And so that's just a background on perovskite nanocrystals. And so one way to, if we're going to be modeling excited state dynamics, we want to have an idea of what electronic structure these materials looks like. And essentially they are just cubes or particles in a box. So simple physical models. So if you consider like Bloch wave functions for a periodic semiconductor, so you have your periodic atomic potentials in your plane waves. But once you go down to a particle in the box, your plane waves essentially just turn into standing waves, so it's a sine function. And your wave functions have your typical solution for a particle in the box. And you can interpret the energies for photo-induced holes and photo-induced electrons using particle in the box solutions, or approximate them as using the standing waves. So this color figure shows the valence band where you have occupied states, and then these very narrow figures show the density of states for your particles, and then these boxes just show what the wave function or the envelope function. So you have your particle in the box, and you have for your lowest excited, for the lowest state, you expect spherical symmetry. And then your next band, you expect p orbital symmetry. So we'll come back.
Question.
Yes.
So in the particle in box, what exactly is this U sub n of r? What is this function?
N of r.
U sub n of r.
Well, it's just a periodic potential, so it's like the atomic lattice.
No, this is a wave function. So what is this U?
Talking about this one here, right?
You mean atomic function in the vicinity of atom?
Yeah, like atomic orbitals. Site centered atomic orbitals, essentially, is how you think of it.
So it's not literally particle in box.
Not literally. So you can. So these don't show the U parts; they just show the envelope functions. But if you made this transparent, you would have like quickly oscillating parts inside of this. So these plots just show the envelope functions. Whereas if we wanted to do these U events that are complicated, so we use software to compete with those, which we'll get to. So it might not seem relevant now, but I just made this slide, so I'm going to call back to it later in some slides.
Satisfied. The equation before the arrow is for bulk. The equation after arrow is after applying confinement.
Is it considered that because it's not really a particle in the box, the energy wouldn't just be kinetic energy?
Well, if it's literally particle in box, then the wave function is proportional to sine k r, with k is being quantized given the energies that they show. And I was just curious what exactly is the physical. Okay, I don't want to describe it. Okay, we'll talk about it later.
Okay. So that's just considering if you put photoexcited carriers in a box, and then typically nanocrystals, they're more covalently bonded, so they don't have ionic charges in them. But these perovskites are a little bit more unique because they're polar crystals, and so instead of excitonic contributions being more dominant in these, it's going to be Polaron. Or Polarons are going to be more prevalent to form in the excited state than excitons. And that's mostly due to the very high dielectric screening in these materials. So Coulomb interactions decay very quickly, so electrons and holes are going to be screened by the lattice-sites compared to being on top of each other. So that's just comparing with these two figures here compared. And so if you have very little dielectric confinement, or small dielectric confinement, you have a photoexcited electron in a hole, and they can be more or less delocalized, and they can interact with each other, while these lattice-sites are charged. They don't move very much from equilibrium. But compared to if you have Polaron formation, you can see that these electron and hole states become a lot more confined. So if you have your electron here, it's going to be pulling positive nuclei towards it more and repelling negatively charged nuclei away, and vice versa for the hole. And so essentially what that does in your spatial coordinate is it localizes your charges into two distinct regimes. And notice that these bound, or you consider them as bound states, and they have these lines represent like electronic states for the bound polaron. And so this is just kind of introducing the idea of polarons in these perovskites. And so the Hamiltonian for polarons in general, if you want to think about how to describe the electronic structure of these, is the Frolich Hamiltonian was the first Hamiltonian used to describe these, so this was back in the 1950s, and so second quantization form. So basically it's made up of three parts. You have your on-site electronic states, you have your independent phonon modes here in the NDSU, and you have the cross-turn electron-phonon couple. Because you put the charge in and it interacts with the nuclei, so that gives its cross-turn here. And so the on-site energies, those correspond to summing up this all your electronic energy. So N is your band state, K is your momentum, and S is your spin density. So you just create a state with a certain energy value. And same thing with your phonons. So you have your phonon momentum and band density. It has a certain energy unoccupied. And then your cross term, this is just the matrix element of the cross term. So you have an electronic state interacting with the phonon state. And for these solutions, the analytical solutions are very hard to come by. So a lot of solutions, they use perturbative or variational schemes. So it introduces this alpha parameter, which people use to characterize the strength of the electron phonon coupling in these solutions. And this kind of indirectly determines the size of the polaron. And so instead of looking into analytical solutions to these, because I'm a pretty simple guy and I haven't done finding pathing growth, so it's kind of hard to understand the literature on this, but a simple way to understand the bound electronic states in these polarons is just to consider a Coulomb interaction. And so this is from a paper by Walter Kohn back in the 1950s. Basically, the point of this paper is that he found that if you introduce an electron or a hole into a semiconductor, you can reformulate the many-body problem into an effective mass problem. So basically, you just have an effective mass with the Coulomb interaction, and that describes the electronic state of the added charge interacting with the nuclei around it. And so any sort of Coulomb problem, we know what the solutions to those look like. They're going to be analogous to the hydrogenic solutions. So if we have our polaron bound states, that's what these represent. This represents the 1 over R potential. These bands represent polaron electronic states in the confinement well. You could approximate or think about these just similarly as you would for a hydrogenic solution. And the energy spaces for each of these states would be some sort of scaled version of the Rydberg energy. Like the energy of your lowest hydrogenic state.
So you have an electron, it polarizes the material rocks. That's the polaron.
Yes.
And then it interacts with it.
So this paper doesn't include the ionic movement, but you can think of it as, you can just do a self-consistent scheme.
What is the hole in the pole? Can you describe Polaron electronic structure in electron hole interaction? So is the hole the polarized charge from the surrounding atoms? Is this how we should think about this?
The way I think about it is you still have your independent electron hole. So your photoexcite, you have your electron hole.
Okay.
But they just interact with different nuclei states because you have positive and negative nuclei charges. So the hole is going to interact more with
Nuclei
negative.
tend to be positive.
Say that again?
Nuclei tend to be positively charged. Electrons tend to be negatively charged.
I guess they're ionic charges. So we can have a positive or a negative. So like halides, they take an electron, and so they have an overall negative charge in the ions. So ions can have positive or negative.
Well, you can shift the charge around, and you will have a build-up of positive charge and negative charge.
Exactly.
So maybe the term nuclei is better, because nuclei is just made up of the. It's not just the nucleus; it's the nucleus and the valence electron atom. And so some atoms they can take an extra charge, and so in the lattice they'll have an overall negative charge.
So first, polarons can be created without a photoexcitation. Charges can be injected, either positive or negative. here he's considering response of a lattice to the injected charge and self-consistent response of this injected charge to the change in the lattice.
That response is the effective hold.
In some communities, instead of effective hold or effective electron, people use the word hold.
And that's what creates this hydrogen like now.
And so it becomes bound. So it's, then it just looks similar to the Coulomb problem.
So I mean, you can have like electron Polaron or home Polaron depends on the system. I'm just confused a little bit about the term hydrogenic that you use here, because when I think about hydrogenic state, I'm thinking about, let's say, silicon doped with aluminum or silicon doped with phosphorus. It introduces very shallow effect near the edge. And if you look at the wavefunctions, it's very standard, very delocalized. So when we think about Polaron, we think about a lot, much more localized wavefunction. Right? So
Well, I guess
I'm a little bit confused about the equivalent between that Polaron wavefunction and hydrogenic wavefunction. Oh, maybe you are right, but confused about the name.
And so Polarons, you can have a lot of different sizes, so there's different regimes. So the ones in these materials, like experimental, they're very large, like 9 nanometers. So it's not a very balanced state, so it has a deeper well, or not, it has a shallower well. And in these, I guess I'm not sure of the exact binding energies, but just from initial computations, it's around 1 eV binding. So it's stronger than like a dopant impurity, but it's still less than the hydrogenic. So it's like, it's in between, essentially. And so we can have electronic states introduced due to a polaron. And people are researching these in the 60s, looking for solutions. One paper I came across found that for an appropriate coupling value, in the paper they found from like 2.5 to 6, that these bound states are stable enough. So you can treat them perturbatively compared to like any sort of excitation that you do. And so since you can treat transitions between these Polaron states perturbatively, you can determine rates between these Polaronic states using essentially Fermi's building law. And so for this presentation, we'll be talking about, or this illustration here just is simulating the absorption spectrum. So you can have a series from this Polaron ground state to this relaxed excited state, and so forth going on. Or you can even have them coupled to conduction band states. So you can also have non-radiative transitions. So in photoexcited, they cascade down too. And so this is essentially what we're going to be trying to be modeling with our atomistic models. And this figure just shows experimentally for a close cousin material, for the ones we're looking at. So they have a little bit different chemistry. And they're not nanocrystals, they're thin films. But they do pump probe experiments to look at time-resolved IR spectra. Here. So essentially the simple idea is that they pump it so they're photoexcited at a high energy, like 2 eV, to create the polaron. And then they probe it with IR frequencies to look for absorption characteristics. And just due to the different chemistry, they see a temperature dependence for polaron absorption. But the results from here indicates that they do see polarons in these materials. And so the next slide just kind of outlines, based on everything that we've done over here, what we're trying to model for dynamics of these systems. So our atomistic model, what we want to do is model a photoexcitation from the conduction band, or valence band to conduction band, monitor the carrier cooling to what's called in the literature usually the Polaron relaxed excited states. And you can have two different states. You can have an electron or a negative Polaron, or called a positive Polaron. And then once they relax to these relaxed excited states, we want to try to determine the non-radiative and radiative transitions between the relaxed excited states to the Polaron ground states. And so this is like our end goal for what we want to model. We're going slowly and a little bit more methodically, so we break them up into just a negative Polaron and positive Polaron first. So, which we'll see later in the presentation. And so just some methodology for how we compute electronic spectra for these materials. So we have to use non-collinear Kohn-Sham or DFT for these, and I'll explain that in a second. So basically, what this equation does is it sums over spin states for the materials, and you get some materials you get spin mixing, so spin's not a good Bob number anymore. And so the solutions to this non-collinear one electron equation is a spinor Kohn-Sham orbital, or a spin orbital. And it's just a two-component vector that's made up of spin alpha or spin beta, spin up and spin down components. And they obey the usual rules that you expect for good orbitals. So they have normality and orthogonality. And the reason that we have to use non-collinear orbitals is because in perovskites they have big relativistic effects due to the light orbitals that experiences large spin-orbit coupling. And so within the software they incorporate relativistic effects. So you have special relativistic effects in spin-orbit coupling. And spin-orbit coupling is the big one because for LUTs it has a very high angular momentum state. And that's what this L represents, the mixing of angular momentum with the intrinsic spin. And so that's why we have to use spinors, so because the spin states are mixed. And this will have important consequences for the electronic states and kinetics of these materials. So those are the orbitals, and then these are the observables, the ground state observables we compute. So we have density states, we compute absorption spectra using the spinors, so we compute a transition dipole between two orbitals, which feeds into oscillator strengths. And oscillator strengths are just a probability of photoexcitation between two states due to coupling to electromagnetic. You can make an absorption spectra from that, and then I'll just note that from the oscillator strengths we can compute a radiative lifetime using Einstein coefficients for spontaneous recombination. So that's a charge neutral model, so with no Polaron. And then to model electronic structure of Polarons, we do the same calculations. So we start from a neutral model. And so that's the independent electronic energy and atomic energy, or phonon energy. So that comes from a charge neutral configuration for n electrons. And to approximate the cross term, the electron-phonon coupling, we either add or remove charges from our model system, or add or remove electrons, and then we let the model optimize this delta R around the new charge. And so it changes the atomic positions due to the new charge. And so that's how we approximate the Polaron formation. And then there's a similar group earlier, I reported this year, that uses a similar methodology as we do. And this is just an example for a positive Polaron. So we remove one charge. So we create a whole state, and then we just re-optimize the model around that charge.
Sorry, question.
Mm-hmm.
So you keeping the occupancies fixed?
Change occupancies.
Why making a charge and not just fix the occupancy, one whole occupied home state and one occupied particle state?
So that's the end goal. So that's to model photoexcitation. That's what we'd have to do. But we're doing it piecewise. So we can imagine injecting a hole, and then eventually it becomes a positive Polaron. And then we also compute doing the opposite, so injecting an electron into the conduction band, and it forms a Polaron. And then, so we're going to get two independent models first, so we can see how the systems observe independently.
So it's going to do no interaction between electron polaron and home polaron.
Right. So we're just trying to isolate if we do see emission from these states, whether it comes from the whole polaron or the positive polaron or negative polaron. So we just do this to be systematic.
Intentionally exclude possible electron direction and look for pure positive, pure negative, because the next step, if the sources are see if they can coexist.
Technically, do you introduce background charge to make sure everything is orbital?
It is included in the software package, yes.
And so those are the orbitals that we use to compute some observables, and then I'll just go over how we model the dynamics in these systems. And so we want to model electrons and phonons interacting with each other that give rise to heat dissipation. And so if you do that, or if you set up the time-dependent Schrodinger equation for that problem, eventually what you run into is this cross-coupling term here, which is called nonadiabatic coupling. And essentially what it does is you have two different electronic states, I and J, and due to time evolution of the nuclei, it mixes them. And that gives rise to heat dissipation and non-radiative effects in these systems. And so this is just a Dirac notation, and then this term here is just showing the spinor, showing that we're using spinners to compute non-adiabatic couplings. And just to emphasize that so you update a time step for one orbitals, and you compare it to the previous orbital. And so whatever overlap that they have, that's kind of proportional to the transition rate between those two orbitals due to the heating. And so this is the most competitive aspect of the modeling that we do. So this was first developed in the group in 2018, and then since perovskites require the spin orbital formation, we've applied it to model perovskite systems. And so that's the novelty behind this. And then what we do to convert these non-adiabatic couplings into rates is just a standard procedure of taking your autocorrelation functions, the non-adiabatic couplings. So you measure essentially how fast they decohere, and then you take Fourier transforms and convert them into rates. And then these rates we incorporate into what are called Redfield tensors. And so this is just the density matrix theory that describes electron-phonon interactions and rates of heat dissipation. And so this Redfield tensor provides the dissipative transitions for the density matrix. And this is just the time evolution of the density matrix from the Louisville equation. And another thing to note is for non-radiative lifetimes, we can approximate the non-radiative recombination as just the matrix element corresponding to the HOMO-LUMO transition or whatever non-radiative transition we're looking for. And just to give an idea of what this Redfield tensor looks like, so it's basically just a matrix. So corresponding to matrix of orbital i's and orbital j's with matrix elements, so that's what the z-axis represents. And the height of these bars represent the range or how fast that the transition occurs between two electronic states. And so essentially, so this plot right here corresponds to HOMO minus 24 to HOMO. So that's essentially determines how fast holes cool. So hole cooling rates, and then these correspond to conduction band states. So these describe how fast an electron will cool. And so those are the rates that are used to compute excited state dynamics. And so now we'll get on to the results, which hopefully should tell a story of how we got to modeling Polarons. And so I never introduced the model before, so this is the atomistic model that we use for our calculations. And so it's a perovskite unit or lattice essentially, so 2 by 2 by 2 lattice, with a certain number of atoms. And then to passivate the surface trap states, or like this wouldn't be very stable by itself, it needs a surfactant. And so we just terminate each of the surface leads with a certain type of ligand, which is counterbalances the charge, and same for the bromides. And these ligands correspond to what's seen experimentally. So this would be like oleic acid and oleoamine if you do experiments. And so we have total number of atoms of about 1,000 and 2,800 electrons, so it's a very massive model. It's quite a bit of computational power. And just a note on how we do our calculations. So we use VAST software via no heavy initial software, and VAST uses periodic boundary conditions. So by default, it uses plane waves, which describe the valence electron, and it uses pseudopotentials to describe core electrons. And then we use a PBH functional.
Boundary conditions. There is a bit of vacuum, right?
Oh yeah. So it's seven angstroms of vacuum. So that's so they should be decoupled from each other. 7 angstroms. On the monitor, it looks like inches. And so we optimize it, do calculations, and so this is what the corresponding density states for this model looks like. And so compared to the particle in the box, or approximate particle in the box that we saw earlier, we see that these near the band edges, it shows distinct peaks, which are similar to SP bands. So that's what these the labels correspond to. So SP and H for the whole, and vice versa for the electron. And for the rest of the presentation, the important thing to notice is for the conduction band, it has a very sparse, a very low density of states near the band edge. And that's due to the very strong spin-orbit coupling. Because if you don't include spin-orbit, or I guess it reduces the bandgap by 0.7. So basically it just takes the density states it has there and spreads them out to a number of larger energy states.
So just because it is predominantly P state from chromium?
Yeah, or from the light. So all the conduction band states are lead P, or 6 PM, and they have very high angular momentum, so they have.
Yeah, because spin-orbit effect is strongest, not as strong as the P orbit.
So, yeah, they have low density states, and the energy difference between this SE and PE states is about, for our model, is about 2 EV subgaps, so that's fairly large. If you consider thermal energy, it's about 30 milli-EV, that's 25 EV. Yeah, so this would be 200 milli-EV, so thermal energy is going to be smaller than that. So you'd anticipate that you might see slower cooling just because you have a mismatch between thermal energy to populate that state and the subgap that's there.
So here, so you can see that these stay as Polarons then?
Nope, this is charge neutral. So this is
No Polaron yet.
yeah. So this was work that we've already published. So just a charge neutral model. And then we're working towards the Polaron. So it'll be a couple more slides for the Polaron. And then, so it's a ground state electronic structure. And then just to make the connection back to particle in the box. So in this left, so this box represents like the boundary conditions. And this sphere on the inside represents the envelope function for particle in the box. And we don't compute the periodic part or the fast variant. But for additional calculations, you look at the orbital, so this is a corresponding orbital for the lowest excited state. You can see, I guess, the plane or the standing wave in symmetry. So this is the model in 3D. So then what this figure shows is the density just projected on the 2D. So we just integrate over X and Y. You can see this would be the U potential here, and then it's not plotted, but you could imagine an envelope function that goes around that. And so, yeah, it's just helpful to know that at least some of the orbitals in these models obey like symmetry. And symmetry is kind of important because you can kind of have a guess of what transitions and some properties of these materials will look like, or what would happen just based on symmetry. And so that's ground state. And so we'll move on to excited state dynamics for this model. Let's have one slide on it. So there's a lot going on here, but basically what this figure represents is the carrier cooling in time. So this is a log scale. So -3 represents 1 femtosecond, and 0 is 1 picosecond. So that's usually the time scale that cooling occurs on. And the green represents charge neutral background, so just ground state. The yellow represents non-equilibrium charge density, so you have a photoexcited electron. And blue represents hole density at these energy states. And the lines just correspond to energy expectation values due to changes in population over time. And so for both these models, we see fairly fast hole cooling. It occurs on 100 femtosecond time scales, and that's kind of in line with what they see in experiments. But the most interesting aspect of this figure, it's kind of hard to see on the state background, but you kind of see a smear as it cools down here, and that kind of indicates that there's population buildup or density buildup as it's trying to cool to the band edge. And so a better way to represent what this plot is, you move it over to this plot. And so this is just a dimensionless energy, so 0 to 1, same time axis. And then this plot here just represents the density of states, just bands for the model. And what's plotted is a single exponential fit. So we just tried to fit the decays to a single exponential, and that's the red dotted line. And if you compare that to what's actually computed over here, you see that there's a fairly faster than normal or single exponential decay. And then it gets to a certain point near the band edge, and this decay slows down considerably. And we attribute that to a large mismatch in density states, or a large slug gap, because thermal energy is going to be much smaller than this gap, so it's going to take a lot longer for it to cool to the band edges. And so that was interesting in itself. Dimitri mentioned we published that in JAX earlier this year. But then if you consider where these density of states are, the energy states, and the fact that we have slower non-radiative cooling, an interesting idea would be to utilize this state here and try to manipulate it into being an emitting state. Since you have a build-up, you have inverse occupations, you can potentially get optical transitions or photoluminescence there. And so that's where we move on to modeling Polarons for these models. And so the two models we'll be talking about here for today are just positive and negative, so just adding and removing charges to our quantum dot model. And so, and for each model, we break it up into 3 submodels. And so if you remove one charge for the positive photon, you get a doublet state, so you have an unpaired spin, which is a doublet. If you remove 2 charges, you can get singlets, so 2 spins along antiparallel, and triplets where the spins align. And then same idea with the negative photon. Add 1 charge, double it, add 2, you can have singlet or triplet. And so this is the ground state electronic structure for the positive photon. And so this is the whole density states for the whole model. And this box top region is what corresponds to here, so we want to look at valence bands, so that's where the hole's going to be. And so you can see in each of these figures, so singlet, double, and triplet, the filled-in regions correspond to occupied states, and then these white figures below the line correspond to unoccupied. So that's where the hole is going to be for both these models. And then we can see the same kind of see the same possible symmetry state. So you could expect that your Polaron orbitals will see some sort of symmetry as well. And so that's what the density of states look like. And this figure here shows the computed IR spectra. So between possible optical transitions within these regions. And we plot them in wave numbers. So our lower energy is to the right, higher energy is to the left. So the lowest energy transition for all these models are indicated with the arrows. And we see for the singlet and the triplet, they're basically the same for lowest energy transition. So they're fairly bright, whereas for the doublet, the lowest energy is fairly dark, and it's higher in energy. So if we're going to look for PL from this system, it would probably be from the singlet or triplet models compared to the doublet. And basically the same figure for the negative Polaron. So instead of looking at valence band, we look at conduction band occupations. So for singlet and triplet, we see the occupied regions. For doublet, it's half filled. And the reason it's half filled is each band is twice degenerate. So it takes 2 charges to fill up that state. And we look at IR absorption again for these materials. So previously it was at 500 wave numbers. These are a bit higher in energy for the lowest energy transitions. We see singlet, triplet are about the same again in intensity and energy. And the doublet is about the same energy, but it's lower in intensity. So it's kind of masked there. So we see the same trend again where we're going to see photoluminescence. It would probably be from the triplet or doublet configurations. And then for the last couple of minutes, we'll look at the dynamics for these Polaron models. And so these are similar green figures as before that we saw. So they just correspond to Polaron cooling. And so I put these visualizations here to kind of help interpret what we're trying to model for these. So you can imagine that we inject a hole, like we hook up some sort of molecular lead, and we just put it in a hole to the valence band. And eventually, that hole is going to cool to that relaxed, excited state for the Polaron and be pretty stable there for a while. And we see both of these models that the cooling occurs pretty much on the same time scale, a couple hundred femtoseconds. Or, yeah, hundreds of femtoseconds. And so we see cooling to the relaxed, excited state. And then our next figure is going to be looking at time resolved and time integrated emission along that excited state trajectory. So it's the same cooling dynamics, except instead of non-radiative transitions, we look at radiative transitions that compete with it. And so if you have a radiative transition that's quicker than the non-radiative, you get counts essentially in this time resolved spectrum. We see that early on in the dynamics, both the models could show a cascading, or 3 separate bands of emission in these states with varying intensity. And you can kind of interpret that as you inject the charge, and then you have cascading of possible optical transitions, and then as you cool further down in the band, essentially are just left with one optical transition, and that's what we see here. So this is cooling to the relaxed excited state, and then just emitting until the non-radiative, up to the non-radiative recombination time scale. And so the big difference between the singlet and the doublet is the singlet, once it cools to the relaxed excited state, the bandgap is about 0.1 eV, and it emits there, whereas for the doublet, it cools and its lowest energy transition is 0 eV, so it doesn't really emit from 0 eV, and so all we see is just the cascading low intensity transition when it cools. And so the last slide is, so if we consider how efficient these positive Polaron emitters are, and so let's just sum up in this table. So this column corresponds to the radiation lifetimes, which just come from Einstein coefficients, And they occur, and their rates occur on the inverse microsecond scale, whereas for the non-radiative transitions, for that lowest energy transition, they correspond on inverse picoseconds. And so essentially, if you just think about how to calculate photoluminescence fundamental, the radiative will be the sum of radiative and non-radiative. And since the non-radiative is 6 order magnitudes quicker, you have very large denominator, and so you have essentially 0 photoluminescence fundamental. And so that just kind of shows that if we're going to see IR emission, it's probably going to come from the negative polaron, which is kind of what we suspected earlier, kind of leading into this project. And so, just to conclude, so in the previous result, we saw there was slow hot electron cooling due to bandgaps. That kind of gave the motivation to use that subgap that caused the slow cooling as an IR source. And just from ground state calculations for the Polaron, we see that we do see bright optical transitions for single and doublet. So it does seem possible that we get photoluminescence from the states if the kinetics match up right. But for the positive Polaron, it's very inefficient, and we have ongoing calculations for the negative Polaron, and we're working towards the charge neutral photoexcited Polaron. And looks like I timed that out pretty well.
Okay. Thanks for the papers of the discussion.
So I try to understand that in terms of the language for physics. So the Polaron we're talking about is some defect level at about 0.2 eV below the valence band, condenser band minimum, and above the valence band maximum. Right? But it's big enough so that it's much. The value is much bigger than the thermal energy. Right?
Mm-hmm. Yep.
So by caloric coolant, you mean the calorie get trapped at that defect level, and it's slowed down a little bit.
Mm-hmm.
That's what you mean by caloric coolant.
Mm-hmm.
Okay.
And so in the non-Polaron picture, we call that slow cooling. Mm-hmm. But as soon as we change our model into considering Polarons, that transition would become the non-radiative recombination. And so we try to utilize that slow cooling as a non-radiative for photoluminescence.
Could you repeat for me the terminology? Positive Polaron is a hole with a little bit of induced charge that grows from the wire, right?
Mm-hmm.
And same for the electron.
Mm-hmm. So that would be a negative electronic charge interacting with like a mean ionic field.
But if you look from far away, the charge which is called the monomer is less than the charge in the electron, right? Because it loses some charge onto it.
Screen.
Screen. No, see, that's where I can. Well, okay. So, also, I'm a little bit difficult to follow. So, when you do your when you run your density functional theory simulations combined with non-radiative couplings, I mean, everything that's going on is already there. Polarons are not, and you look at the K-air cooling and so on and so forth, and then you kind of switch gears and you talk about Polarons. Low scale, what changed?
So I guess it's just running the same machinery for a nonadiabatic coupling, so it's just different charge occupations. So a charge neutral, it's like we wouldn't have any occupancy in the conduction band when we do our calculations for nonadiabatic couplings. But when we do the Polaron, we occupy the lowest conduction band state, and then do the same
When you say, when you say neutral, what do you have? I'm really confused here. I mean, I thought, okay, you occupy hole, there's a hole, there's an electron, and you let it, evolve with time. It interacts with the thermal motion of ions in whatever way it will. Should there be Polarons or not? So, there.
They had a comment that we could translate between two areas. If one is approaching computational modeling of a molecule or material, at the first step, one assumes that the number of electrons in the modeling is equal to the total positive charge of all ions.
Well, assuming that the material is neutral.
But there is an option to change total number of electrons, and we can compute both Perovskite, dynamics, some celestial properties in presence of charge imbalance.
Right. And that stands for this photoexcited electron and the holes, who knows where. We don't know anything about it.
It doesn't need to be fully excited. It can be injected charge.
Oh, okay, so you're not talking about photoexcitation.
Not yet. We're working towards the photo excitation.
So it's an electron moving through this port here.
And getting dressed in a court of performance.
So in the case of nanocrystal, you have something that you call Polaron. Do you also have Polaron in the case of a bulk crystal?
Yeah, but it's just, the Polaron is just intrinsic to the polar crystal structure itself. So no matter what dimensionality, in some sense, you would expect, there's a possibility to see Polaron formation. I guess it hasn't been experimentally shown in perovskite nanocrystals yet, but there's some evidence, well, at least to me that seems kind of useful to think that there's Polaron occupations there.
You may want to check it with calculation. Yeah. Because I'm thinking about whether, when you go to small system, because of the quantum confinement effect, rather than wavelengths and small localized, when you pull out 1 electron or 1 electron.
So yeah, these would be small Polarons compared to what would be seen experimentally. But I guess it's the best we can do at the moment, just because of the number.
I'm not talking about the size of the system in the calculation. Because it's 1,000 atom and more than 2,000 electron. I think that's enough for us to do it. But I'm thinking about when you go to a smaller system, nanocrystal, because of the confinement effect, the subgap space, the Polaron space, can be more localized than in the bulk. That's something you will want to look at.
You're correct, but it is like hard to postulate. So if one would consider, if one would consider Polaron in the periodic bulk material, then one needs to take into account non-zero momentum in the traveling Polaron, which adds additional degree of freedom. So one needs to do periodic boundary condition calculations. One needs to recompute it at different k points. It will be much harder.
It doesn't have to. It doesn't have to. I'm thinking about some transition metal oxide. If you pull out 1 electron, you can see a small Polaron almost right there.
That's correct. But in this material, it will be traveling Polaron.
Yeah. Because in this case, you may not have a small Polaron, but you have a large Polaron, and you may need to do a very system. Yeah.
Sorry to ask so many questions. I'm really curious. Very interesting. Can you please show me your conclusion slide? Well, okay, maybe.
Almost there. Okay.
Okay, due to blah blah blah, we try to utilize large subgap as an IR emission source. Can you please put it very quick for me? It's kind of missing the idea. What do we combine with what? A particle has to be combined with a cold, right? And data for
Mm-hmm.
No, no.
Yeah.
Let me translate once again. So, common vision of emitting semiconductors that they emit because of the particle hole with radiative recombine from conduction band to valence band, from meters. If the system is charged with either positive or negative charge, is injected, then it will be a recombination of particle and hole, but their